Right now, the light reaching your eyes from the nearest large galaxy has been traveling for 2.5 million years. It left its source before your species existed, before the first stone tool was shaped by the first careful hand, before language, before fire, before any ancestor of yours had looked up at a night sky and felt the particular silence that comes from not knowing what the distant lights are. That light crossed a void so absolute, so overwhelming in its physical character that the word emptiness cannot contain what it describes. And it arrived here, at this moment, entering your eye, after a journey that makes the entire span of human civilization look like the space between two heartbeats. That single fact should stop you cold, but it does not tell you the whole truth, because 2.5 million light years sounds like a measurement. It sounds like something that can be grasped the way you grasp the distance between two cities or the depth of an ocean trench or the height of a mountain range. It sounds large but ultimately manageable. It sounds like a challenge that a sufficiently advanced civilization might one day meet. It is not a challenge. It is a verdict delivered by the deepest laws of physics. And the more carefully you examine what that number actually means, what fills the space it describes, and what the laws of nature permit to cross it, the more that verdict solidifies into something permanent. Something that no amount of ingenuity or ambition can overturn. The universe is not merely large, it is organized at its most fundamental level to ensure that its largest structures remain forever isolated from one another. Not by accident, not as a temporary condition awaiting a clever enough solution, by the architecture of reality itself. 2 trillion galaxies drift within the volume of space our telescopes can reach. 2 trillion islands of stars, each containing hundreds of billions of suns, each one potentially orbited by trillions of worlds. The universe is by any reasonable measure extraordinarily full of structure. And yet if you were to ask what the universe is fundamentally made of, if you were to measure not by the number of objects but by the volume they occupy, the answer would not be stars. It would not be galaxies or planets or nebulae or any of the luminous structures that fill our telescopes and our imaginations. The answer would be nothing. 80% of the observable universe by volume is void, empty, structureless. A darkness so vast and so complete that every galaxy ever catalogued, every star ever observed, every planet ever detected, amounts to a thin luminous residue clinging to the surface of an architecture built almost entirely from absence. The photographs you have seen, the deep field images crowded with thousands of galaxies, the sweeping panoramas of cosmic structure, they are telling you a story about the universe that is beautiful and true in its details, and profoundly misleading in its overall impression. The universe is not full. It is the loneliest structure that has ever existed. If these are the kinds of questions that pull at you, questions that dissolve the floor beneath everything you thought you understood about the place you inhabit, do me a small favor and hit that like button and subscribe. It genuinely helps this channel keep making these journeys, and I am grateful for every one of you who comes along. Now, settle in, get yourself comfortable. Let's begin. Look at any image taken by a powerful space telescope pointed toward the deep universe. The James Webb Space Telescope, with its gold-plated mirrors and infrared sensitivity, capable of detecting the heat of a single candle flame at the distance of the moon. The Hubble Space Telescope, which spent over 3 decades collecting light from the farthest reaches of the observable cosmos. Point either of these instruments at a patch of sky, dark enough and small enough that you could cover it with a grain of sand held at arm's length. Keep the shutter open long enough, and what fills the frame will take your breath away. Galaxies, hundreds of them, thousands, spirals whose arms trail starlight like the wake of something enormous moving through still water. Ellipticals glowing amber and gold with the combined radiance of billions of aging stars. Irregulars twisted and asymmetrical, the scarred survivors of ancient collisions still slowly settling into new shapes after billions of years of gravitational rearrangement. The images are extraordinary. They are also, in one very precise and very important sense, a form of deception. Not intentional deception. The telescopes record faithfully what arrives at their detectors. The images are accurate representations of the light that traveled across the universe and landed on the instrument. The deception is not in the data. It is in what happens between the data and your brain. Because your visual system, the product of millions of years of evolution on the surface of a small planet, was never designed to interpret images of the deep cosmos. It was designed to navigate a world where the farthest visible object is a mountain range a few dozen miles away, and when it encounters a deep field photograph, it applies the same rules it would apply to any other visual scene. Objects that appear close together must be close together. Objects that appear smaller must be farther away. The arrangement of things in the frame reflects their arrangement in space. Every one of those assumptions fails catastrophically when applied to a photograph of the universe. Two galaxies that appear side by side in a deep field image might be separated by 100 million light-years of void. A galaxy that looks only slightly smaller than its neighbor might be 10 times more distant. The image collapses billions of light-years of three-dimensional space onto a flat sensor, and then displays that collapsed depth on a flat screen, and your visual system fills the missing dimension with proximity, with warmth, with the comfortable illusion that the galaxies you see are neighbors in some meaningful sense of that word. They are not neighbors. They are prisoners of their own locations, separated by distances so vast, an environment so utterly barren that the word separation barely begins to capture the reality. And to understand why you first need a ruler, you need to establish the scale of a single galaxy before the gaps between galaxies can register at anything approaching their true magnitude. Because the distances between galaxies are measured in multiples of galaxy lengths, and until you feel the weight of a single galaxy length in your bones, the multiples will remain numbers rather than truths. The Milky Way is your home. It is the gravitational community your sun belongs to, the spiral structure whose center lies approximately 26,000 light-years from the position of our solar system in one of its outer arms. It contains somewhere between 200 billion and 400 billion stars. Data from the European Space Agency's Gaia spacecraft, which has spent years mapping the positions and velocities of nearly 2 billion individual stars with extraordinary precision, suggests the higher end of that range is closer to the truth. Each of those stars is a thermonuclear furnace. Many are orbited by planets. Some of those planets exist in the temperature range where liquid water can persist on a surface. Some of those surfaces may already host chemistry complex enough to ask its own questions about the night sky above it. The Milky Way spans approximately 1,000,000 light-years across edge to edge. More recent surveys incorporating the galaxy's faint outer halo push that number toward 2,000,000 light-years. Even the conservative figure is enough to break intuition entirely. A light-year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In a single second, a photon could circle the entire Earth 7.5 times. In 8 minutes, that same photon reaches the Sun. In roughly 4 hours, it crosses the orbit of Neptune. In just over 5 hours, it passes Pluto. In 4 years and 3 months, it arrives at Proxima Centauri, the nearest star to our own, a faint red dwarf burning quietly in the dark, 4.24 light-years away. Hold that speed in your mind. The fastest thing the universe permits, the absolute ceiling on how quickly any signal, any object, any piece of information can travel through space. At that speed, crossing the Milky Way takes 1,000,000 years. When the light now leaving the far edge of our galaxy began its journey toward the other side, anatomically modern humans had not yet developed written language. The first permanent settlements were still 9,000 years in the future. The cave paintings at Lascaux, those extraordinary ochre horses pressed into limestone by firelight 17,000 years ago, would not be created for another 8,300 years. The entire span of recorded human history, every civilization, every war, every scientific discovery, every work of art, every line of philosophy ever committed to paper or stone or memory, all of it occupies less than 6% of the time it takes light to cross the structure you were born inside. This is the size of a single galaxy, not the largest known, not some exceptional outlier at the extreme end of the cosmic distribution. A fairly ordinary barred spiral, one of perhaps 100 billion such structures in the observable universe of middling size and unremarkable position, and it takes light 100,000 years to cross it. Now look up. If you are in the northern hemisphere on a clear autumn night, find the constellation Andromeda. Trace the chain of stars that marks its boundary and locate the faint smudge of light sitting just off that chain. Faint enough that light pollution in most cities makes it invisible, but from a dark enough location on a clear enough night, it is there. A pale oval glow utterly unremarkable to the naked eye, easily mistaken for a wisp of cloud or a slight irregularity in the darkness. That smudge is the Andromeda Galaxy. It contains approximately 1 trillion stars. Its disk stretches across somewhere between 2,000,000 and 2,600,000 light-years, making it comparable in size to our own Milky Way and by some measurements somewhat larger. At its center sits a supermassive black hole with a mass estimated at more than 100 million times that of our Sun. It hosts thousands of star clusters, billions of planetary systems, and a complex gravitational architecture of satellite galaxies orbiting its outer edges like moons around a planet. By every reasonable measure, Andromeda is not a small neighbor. It is a complete galactic empire, as vast and as complex as our own, situated across a gulf of space that makes the size of both galaxies feel almost irrelevant. Andromeda is 2.5 million light-years away. Say that number slowly, not as a string of syllables but as a physical fact. 2.5 million light-years. The Milky Way, your home, spans 1,000,000 light-years. Andromeda sits at a distance 25 times the full width of your home galaxy. If you shrank the Milky Way to the size of a dinner plate, Andromeda would sit roughly 25 plate widths away. That sounds manageable, until you remember that the dinner plate in this analogy contains 400 billion stars and takes light 1,000,000 years to cross. The Parker Solar Probe became, in December of 2024, the fastest human-made object in history. Swinging around the Sun at its closest approach, it reached a velocity of approximately 4,300,000 miles per hour. At that speed, it could travel from New York to Tokyo in under a minute. It could circle the entire Earth in roughly 3.5 minutes. This is the pinnacle of human engineering applied to the problem of velocity. The absolute fastest any machine our species has ever built has ever moved. At that speed, the journey to Andromeda would take approximately 4 billion years. Not 4,000, not 4 million, 4 billion, the current age of the Earth. You would travel at the fastest velocity humanity has ever achieved without stopping, without slowing, for a duration equal to the entire geological history of our planet, and you would arrive at a galaxy that astronomers describe as our nearest large neighbor. Even light needs 2.5 million years. A laser beam fired at Andromeda today would not arrive until the year 25,02026. Whatever sent that signal, whatever civilization aimed that laser at the Andromeda sky, whatever question it hoped to ask the answer, could not return for 5 million years. No conversation is possible. No exchange of any kind. The distance does not merely make travel difficult. It makes communication in any meaningful sense of that word impossible. And here is the detail that truly ruptures intuition. Andromeda is close. By the standards of intergalactic distance, by the scale at which the universe measures its own geography, Andromeda is practically adjacent. It is the nearest large spiral galaxy to our own. When astronomers construct lists of our galactic neighbors, Andromeda is always first. It is the most massive member of our local gravitational family, the structure most likely to interact with us in the cosmic future, in roughly 5 to 7 billion years. Andromeda and the Milky Way are expected to collide and eventually merge into a single massive elliptical galaxy. They are already falling toward each other at approximately 2,500,000 miles per hour, a trajectory confirmed through decades of spectroscopic measurement and proper motion data from the Gaia satellite. Two galactic empires, each spanning hundreds of thousands of light-years, each containing hundreds of billions of stars locked in a slow gravitational embrace that has been tightening for billions of years. And the gap between them right now is still 2.5 million light-years of nearly empty space. The photons entering your eye when you look at that faint smudge in the autumn sky left Andromeda's stars before the genus Homo existed on Earth. Before Homo habilis, before Homo erectus, before any creature that would eventually become you had yet appeared in the fossil record. You are not seeing a galaxy as it exists today. You are seeing a message written in light 2.5 million years ago, crossing a void that makes the entire history of your species look like a footnote and arriving at your eye in this moment as though it had somewhere specific to be. The Milky Way or your Andromeda are not alone. They belong to a gravitational association called the Local Group, a family of galaxies bound together by their mutual attraction. Current surveys count approximately 134 confirmed members. The majority of these are dwarf galaxies, small, irregular structures containing only a few billion stars, many of them orbiting the Milky Way or Andromeda as satellites the way moons orbit planets. The third largest member, the Triangulum Galaxy, contains roughly 40 billion stars and sits about 2.7 million light-years from us. Beyond these three dominant spirals, the local group thins rapidly into scattered dwarfs and isolated irregulars. The local group occupies a volume of space roughly 10 million light-years in diameter. 10 million light-years, 100 times the width of the Milky Way itself. This is our neighborhood, the tightest gravitational community we belong to, the region of space within which our galaxy has meaningful connections to other structures, and it is already so large that the concept of neighborhood has lost all human meaning. There is a word that gets used too casually when people talk about space: empty. We say that space is empty, the way we say a room is empty when the furniture has been moved out. The way we say a street is empty on a Sunday morning before the city wakes up. The word implies an absence that is temporary, incidental, a condition that exists only because the things that should fill a space happen to be somewhere else at the moment. Empty in ordinary language means waiting to be filled. The space between galaxies is not empty in that sense. It is empty in a way that has no analogy in ordinary human experience. Empty in a way that requires an entirely new category of understanding, because the void between galaxies is not merely a region where matter happens to be absent. It is a region where matter has been systematically evacuated over billions of years by the same gravitational forces that built the galaxies themselves. It is a void so complete, so physically extreme, and so overwhelming in its scale that the most sophisticated vacuum chambers ever built by human hands, the gleaming steel vessels inside particle accelerators and semiconductor fabrication facilities that represent the absolute pinnacle of our ability to remove matter from a confined volume, would register as a dense, crowded, almost atmospheric environment by comparison. This is not a metaphor. This is a measurement. Begin with the air around you, the room you are sitting in right now. The atmosphere you are breathing without thinking about it contains approximately 25 trillion molecules of gas in every cubic meter. That number, 25, followed by 24 zeros, is already beyond comfortable comprehension, but hold it as a reference point. It is the density of the environment your body was built to inhabit. Now step outside the Earth's atmosphere entirely, into the space between planets, into the volume of the solar system beyond the protective bubble of our magnetosphere. The density there drops to roughly 5 million particles per cubic meter. Still a vacuum by any earthly standard, far too thin to breathe, far too sparse to conduct heat in any meaningful way, but still a genuine medium, still a place where particles are present in numbers large enough to influence spacecraft, to carry the solar wind to create auroras when they strike planetary magnetic fields. Step farther, cross the boundary of the solar system into the interstellar space of the Milky Way, into the vast regions between stars. The density there drops again to roughly 1 million particles per cubic meter in a typical interstellar cloud, and sometimes as low as a few 100,000 in the more diffuse regions between spiral arms. This is the interstellar medium, the thin gas and dust that permeates the body of our galaxy, and it is so sparse that the best vacuum chambers on Earth cannot replicate it. A laboratory vacuum good enough to conduct precision particle physics experiments contains roughly 10 trillion molecules per cubic meter. Interstellar space is a billion times emptier than that. At this point, most people feel that they have reached the floor. That interstellar space represents the limit of physical emptiness, the baseline condition of the universe, away from the warm, dense exceptions of planetary surfaces and stellar interiors. They are wrong. The space between galaxies is 1 million times emptier than the space between stars. Not a little emptier, not significantly emptier. 1 million times. The jump from interstellar space to intergalactic space is not a step further along the same ladder. It is a leap into a completely different category of emptiness, a qualitative transformation so extreme that the comparison requires a moment to absorb. In a typical region of intergalactic space, the density of matter drops to approximately 1 atom per cubic meter. 1. A single hydrogen atom rattling around alone in a volume the size of a large washing machine with nothing for company and no prospect of encountering another atom in any direction for distances that dwarf the solar system. The rest of that cubic meter, the overwhelming, crushing, absolute majority of it, contains nothing at all. To feel what that means, try this. Hold out your hand, open your palm. The volume of air above your palm, the space between your skin and the ceiling above you, contains more molecules than all the atoms in all the stars in the Milky Way. The air in a single breath contains roughly 10 times more molecules than there are stars in the observable universe. The matter density of the world you inhabit is so incomprehensibly greater than the matter density of intergalactic space that any attempt to compare them directly produces numbers that stop functioning as numbers and become pure abstraction. 1 atom per cubic meter. That is the intergalactic medium in its densest typical regions. In the deep voids between galactic filaments, the density drops even further to fractions of a single atom per cubic meter, to regions where the concept of a particle density becomes almost meaningless because the particles are so few and so far apart that their individual existence matters more than their collective properties. For decades, this picture of intergalactic space presented cosmologists with a serious problem, not because they doubted the emptiness, but because the emptiness was hiding something. When astronomers in the late 20th century began carefully accounting for all the ordinary matter in the universe, the protons and neutrons and electrons that make up every atom of every visible structure, they found a discrepancy. The cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, told them precisely how much ordinary matter the universe was born with. The laws of nuclear physics in the first minutes after the Big Bang determined the ratio of hydrogen to helium to lithium with extraordinary precision, and those ratios locked in the total quantity of ordinary matter that has existed in the universe ever since. When they added up all the matter, they could find matter in stars, in gas clouds, in galaxy clusters, in the diffuse gas within galaxies. They could account for only about half of what the universe was supposed to contain. The other half had vanished. Roughly half of all the ordinary matter in the universe was simply missing, unaccounted for, invisible to every instrument pointed at every corner of the sky. This missing matter became one of the most significant open questions in astrophysics. Where was half the universe? The answer, confirmed through a series of observations culminating in the late 2010s and early 2020s, was both elegant and deeply strange. The missing matter was in the intergalactic medium, not concentrated into visible structures, not hiding inside galaxies or clusters or any of the bright things our telescopes were designed to detect. It was spread across the enormous volumes of space between galaxies, heated to temperatures between 1,000,000 and 10 million degrees, by the shock waves generated during the formation of cosmic structure, and dispersed so thinly that it had been effectively invisible to every previous generation of instruments. This material has a name, the warm-hot intergalactic medium, and it is one of the most extraordinary substances, if substance is even the right word, that the universe contains. Its temperature sounds impossibly high, between 1,000,000 and 10 million degrees, hotter than the surface of the sun, hotter than the corona of the sun, temperatures that in any ordinary context would imply a plasma of ferocious energy and violent activity. But temperature in physics does not measure how hot something feels. It measures the average kinetic energy of individual particles, the speed at which those particles are moving, and when those particles are separated by meters of empty space, when there are so few of them that a cubic meter contains only a handful, the total thermal energy in any given volume is negligible. You could float in the warm, hot intergalactic medium and freeze to death, surrounded by particles moving at millions of miles per hour, each one technically hotter than the sun's surface, but so few and so far apart that they would almost never collide with your body, almost never transfer their energy to you, almost never register as warmth of any kind. The temperature is real, the heat is not. The void between galaxies is simultaneously, in a precise physical sense, one of the hottest and one of the coldest environments in the universe. The confirmation of the warm, hot intergalactic medium came in stages. In 2018, observations of highly ionized oxygen atoms detected in the spectra of distant quasars, those extraordinarily luminous cores of active galaxies whose light serves as a cosmic backlight, provided strong evidence that this diffuse plasma threads along the lines of sight between Earth and these remote light sources. In 2020, measurements of fast radio bursts, brief and enormously energetic pulses of radio waves, originating from distant galaxies, provided a different kind of confirmation. As these pulses travel through the intergalactic medium, the free electrons they encounter slow different frequencies by different amounts, smearing the pulse in a way that reveals how much material it passed through. By analyzing hundreds of these bursts from galaxies at different distances, astronomers were able to reconstruct the density of the intergalactic medium along different lines of sight and confirm that the missing ordinary matter was there dispersed across the void in quantities consistent with theoretical predictions. Roughly 40 to 50% of all the ordinary matter in the universe, half of every proton and neutron that has existed since the Big Bang, resides in this impossibly thin plasma threading between galaxies. Half the universe's ordinary matter, suspended in a medium so diffuse that it took decades of increasingly sensitive instruments to detect its existence at all. And even accounting for all of it, even adding together every atom of the warm, hot intergalactic medium, along with every star in every galaxy and every gas cloud in every cluster, the density of intergalactic space remains so low, the emptiness is not meaningfully reduced. Finding the missing matter did not make the void less void. It revealed that the void is full of something so thin and so ethereal that it barely qualifies as matter in any intuitive sense. The missing half of the universe was missing because it had been smeared across volumes too vast for matter to remain dense enough to see. There is a way to make this concrete that requires no mathematics. Imagine you could take a perfect cubic kilometer of intergalactic space, a volume roughly the size of a large mountain, and compress it. Squeeze all the matter inside that cubic kilometer into the smallest possible volume, pressing every atom together until they touch. The resulting object would be invisible to the naked eye. Not small, but visible. Invisible. The total mass of ordinary matter inside a cubic kilometer of intergalactic space is so negligible that if you compressed it to the density of water, the resulting droplet would be smaller than a bacterium. 1 cubic kilometer of mountain-sized space, compressed to a droplet smaller than a living cell. This is the physical environment that separates every galaxy from every other galaxy. Not a corridor, not a passage, not a medium through which things move the way ships move through water or signals move through wire. A near-perfect vacuum stretched across millions of light years, so empty that the matter within it is functionally indistinguishable from nothing heated to extreme temperatures by ancient shock waves, but carrying so little total energy that it could not warm a cold hand, threaded by the faintest possible traces of a plasma that spent decades evading detection by the most powerful instruments humanity has ever constructed. This is what lies between the Milky Way and Andromeda, between Andromeda and Triangulum, between every galaxy in the local group and every other. Not nothing technically, but something so close to nothing that the distinction requires instruments of extraordinary sensitivity to establish. And the local group, remember, is the tightest galactic community in our cosmic vicinity. These are galaxies bound together by gravity, falling toward each other across millions of light years, eventually destined to collide and merge. If any galaxies in the universe can be described as connected, it is these. And even here, even among gravitational partners confirmed to be in each other's future, the space between them is a void of such completeness that no human technology has ever come close to replicating its emptiness, and no human mind was designed to feel what it actually means to be inside it. Step outside this gravitational family and the void deepens. The density does not simply increase with distance from the local group. It restructures. The character of the emptiness changes, organized not randomly but according to a pattern that took billions of years of gravitational physics to produce, and that reveals something even more unsettling about the architecture of the universe than the simple fact of its emptiness. The void between galaxies is not uniform. It is not a featureless ocean of equal emptiness, stretching in every direction without variation. It has structure, and that structure is the most terrifying thing about it, because the structure is made almost entirely of nothing. The universe is not randomly empty. That distinction matters more than it might initially seem. A random emptiness would be a passive thing, a simple absence of matter, distributed without pattern across the cosmic volume, the way dust settles unevenly across a floor with no particular organization. Random emptiness would be unremarkable. It would be the natural consequence of matter being spread thin across a large space, and it would carry no deeper meaning about the nature of the cosmos. The emptiness of the universe is not random. It is organized. It has geometry. It has been shaped over 13.8 billion years by the most fundamental force in nature into a pattern of such extraordinary complexity and such devastating implication that cosmologists have given it a name that barely captures what it actually is. They call it the cosmic web. And the moment you understand what the cosmic web actually looks like, what it is made of, and what it is mostly made of, the universe becomes a fundamentally different place from the one you thought you inhabited. Begin at the beginning, not the beginning of the universe, but the beginning of structure within it. In the first fraction of a second after the Big Bang, the universe was a uniform, featureless plasma of extraordinary density and temperature. Not perfectly uniform. Nothing in physics is ever perfectly anything. Quantum mechanics, the set of rules that governs the behavior of matter and energy at the smallest scales, ensures that even in the most homogeneous environment imaginable, there are fluctuations, tiny random variations in density, regions where the energy of the infant universe was infinitesimally higher or lower than the average surrounding it. These fluctuations were almost incomprehensibly small. The variation in density across the early universe was roughly 1 part in 100,000. If you represented the average density of the newborn cosmos as a perfectly calm lake, the fluctuations would correspond to ripples less than a millimeter high across a surface, stretching from one end of a continent to the other. Variations so subtle that measuring them required some of the most sensitive instruments ever built. Detecting the faint temperature differences, they left imprinted on the cosmic microwave background radiation. Gravity took those ripples and spent the next 13 billion years turning them into everything you have ever seen. Regions that were infinitesimally denser than average exerted slightly stronger gravitational pulls on surrounding matter. They drew in additional material from adjacent regions. As they grew denser, their gravitational influence grew stronger, pulling in more matter from greater distances. The process fed on itself a gravitational cascade that transformed 1 part in 100,000 density variations into the dramatic structured cosmos we observe today. The regions that lost matter to their denser neighbors became emptier. As matter drained away from them, their gravitational influence weakened further, making it easier for the remaining matter to be pulled toward the growing concentrations. The overdense regions grew denser. The underdense regions grew emptier. Over billions of years, this process carved the universe into 2 fundamentally different kinds of place: the places where matter is and the places where matter is not. The places where matter is form the cosmic web. long thin filaments of dark matter and gas stretching across tens or hundreds of millions of light years, connecting at nodes where multiple filaments intersect into dense concentrations of matter. Galaxy clusters form at these nodes the largest gravitationally bound structures in the observable universe, containing thousands of galaxies and masses measured in quadrillions of solar masses. Where filaments meet at broad angles, they form walls, vast sheet-like concentrations of galaxies that can extend across hundreds of millions of light years while remaining remarkably thin in the perpendicular direction. The whole structure resembles, when mapped in 3 dimensions, a foam or a sponge, or the interior of a bone where dense material forms a rigid lattice surrounding hollow spaces. The hollow spaces are the voids, and the voids are what the universe is mostly made of. A typical cosmic void measures between 30 and 300 million light-years across, not the distance across a void's widest point, the typical diameter. The average size of the hollow spaces between the filaments and walls of the cosmic web, 30 to 300 million light-years of space, containing almost no matter, almost no galaxies, almost no structure of any kind. Just the faintest traces of the warm, hot intergalactic medium drifting through an emptiness so complete that the word empty begins to feel inadequate. The largest confirmed voids exceed 300 million light-years in diameter. Hold that against the size of the Milky Way. Our galaxy spans 1,000,000 light-years. A single large cosmic void is 3,000 times wider than our entire galactic home. If you shrank the Milky Way to the size of a coin, a void of 300 million light-years would be roughly 3 kilometers across. Not 3 kilometers as a metaphor. 3 kilometers of physical space representing a region of the real universe where almost nothing exists. No stars, no galaxies, no planets, no chemistry, no warmth, no story of any kind. And collectively, these voids account for approximately 80% of the total volume of the observable universe. 80%. When you look at the cosmic web mapped in 3 dimensions, when you see the filaments and walls rendered as bright threads against a dark background, your eye is drawn to the structure, to the bright parts, to the places where galaxies cluster and matter concentrates. That is what your visual system does. It finds the signal in the noise, the pattern in the chaos, the object in the background. But the background is the point. The dark parts of the cosmic web are not the background. They are the foreground. They are the dominant feature. The filaments and walls and clusters that draw your eye are the exceptions, the thin, luminous residue that gravity managed to concentrate out of an ocean of primordial gas, leaving behind an ocean of emptiness that is vastly, overwhelmingly, structurally larger than the concentrations it surrounds. The universe is not a room full of galaxies with some empty space between them. It is an ocean of emptiness, with galaxies clinging to the surface of enormous bubbles, like soap foam floating on dark water that has no bottom and no shore. There is a place in the universe that makes this architecture impossible to deny. In 1981, a team of astronomers led by Robert Kirshner at the Harvard-Smithsonian Center for Astrophysics was conducting a survey of galaxy redshifts, measuring the velocities of galaxies in different directions to map large-scale distribution of matter in the local universe. They expected to find galaxies distributed more or less evenly across the volume they were mapping, with some clustering here and some rarefaction there, but nothing dramatically different from the average. What they found instead was a hole. In the direction of the constellation Boötes across a region of sky, they had expected to contain a normal distribution of galaxies. They found almost nothing. A vast spherical region of space stretching across approximately 330 million light-years in diameter, containing only a handful of galaxies, where the average cosmic density would predict roughly 2000. The Boötes void, 330 million light-years across. To cross it at the speed of light would take 330 million years. To cross it at the speed of the Parker Solar Probe, the fastest human-made object ever built, would take approximately 440 trillion years. The entire current age of the universe is 13.8 billion years. Crossing the Boötes void at our maximum velocity would require roughly 32000 times the current age of the cosmos. Inside this enormous volume, astronomers have catalogued approximately 60 galaxies. 60. In a region 3000 times wider than the Milky Way, containing a volume of space so vast that our entire local group, all 134 of its member galaxies, could be copied and pasted into the Boötes void, roughly 200,000 times before it started to feel crowded. 60 galaxies. The few that do exist inside the Boötes void are not scattered randomly across its interior. They cluster in a thin tubular arrangement running through the void's central region as though they are clinging to one final thread of structure, the last remnant of a filament that was almost entirely evacuated by the gravitational drainage that created the void in the first place. These void galaxies are isolated in a way that makes the isolation of typical galaxies look almost sociable. They drift through the emptiness with no near neighbors, no gravitational partners, no passing galaxies to trigger star formation through tidal interactions. They evolve slowly, quietly, in a state of near-total cosmic stasis, the loneliest galaxies in a universe full of lonely galaxies. But the detail about the Boötes void that should stop you completely is not its size or its emptiness, or even the isolation of the galaxies within it. It is what the void would mean for a civilization unlucky enough to have formed inside it. Think about the history of human astronomy. For most of our species' existence, we believed the Milky Way was the entirety of the universe. The great debate about whether the fuzzy spirals visible through early telescopes were nearby gas clouds within our galaxy or distant island universes comparable to our own was not resolved until 1923, when Edwin Hubble measured the distance to what was then called the Andromeda Nebula and found it to be nearly 1 million light-years away, far beyond any possible boundary of the Milky Way. That single measurement shattered the old cosmology and revealed a universe incomparably larger and more complex than anyone had imagined. It was possible, it was achievable, because Andromeda is 2.5 million light-years away, close enough that its individual stars are resolvable with a sufficiently powerful telescope, close enough that the distance can be measured using variable stars whose pulsation, a period, reveals their true luminosity. A civilization inside the Boötes void would never have that moment. Looking outward from any star within the void in any direction, a telescope of any power available to a civilization at our level of development would see nothing beyond the void's sparse interior. The nearest galaxies on the void's boundary sit hundreds of millions of light-years away, so distant and so faint that detecting them would require instruments far beyond anything humanity currently possesses. For most of that civilization's astronomical history, pointing a telescope at the sky would reveal only their own galaxy's stars. They would look outward and see nothing. No Andromeda, no hint of other island universes, no fuzzy spirals to debate, no variable stars in distant galaxies to measure. The universe beyond the void would be invisible not because it does not exist, but because the void is so large and so empty that the light from its boundaries is too faint and too distant to reach the interior with any detectable intensity. From ordinary astronomical instruments, their cosmology would stall. They might develop sophisticated physics, elegant mathematics, a deep understanding of the stars within their own galaxy. But they would have no way of knowing that those stars were just one galaxy among trillions. The void would hide the truth from them not by destroying the evidence, but by placing it so far away that it falls below the threshold of detection. Their entire conception of the universe would be wrong, and they would have no way of knowing it, because the universe had placed them in a location where the evidence for the larger truth was permanently out of reach. The void would not just isolate them physically, it would isolate them epistemically, hiding the very existence of the larger cosmos behind a wall of emptiness too wide for their telescopes to penetrate. The Boötes void is not unique. It is simply the largest and most dramatic confirmed example of a structure that pervades the entire observable universe. Every direction you look mapped in 3 dimensions reveals the same pattern: bright filaments and walls of galaxies surrounding enormous dark bubbles of near-total emptiness. The KBC void, the large underdense region in which our own local group appears to reside, stretches approximately 2 billion light-years across, with a matter density roughly 20% below the cosmic average. The local void, an emptier region adjacent to our galactic neighborhood, extends roughly 150 million light-years and exerts a measurable gravitational influence on the motion of our galaxy, pushing the Milky Way away from its center hundreds of thousands of miles per hour. Wherever astronomers map the three-dimensional distribution of galaxies, they find the same architecture. The voids are not holes in the structure. The voids are the structure. The filaments and walls and clusters are the minority, the thin, luminous exceptions to a rule of overwhelming emptiness that governs the vast majority of cosmic volume, and the voids are not static. This is the detail that transforms the cosmic web from a description of how the universe looks into a description of where it is going. The voids are growing, not slowly, not imperceptibly, actively, measurably, continuously enlarging as the expansion of space proceeds. Inside dense regions, inside galaxy clusters, and along the filaments of the cosmic web, gravity is strong enough to resist the expansion. Galaxies in clusters remain bound to one another. The expansion of space is overcome locally by the mutual gravitational attraction of the structures themselves. These regions do not expand, they hold. But inside voids where matter is sparse and gravity is correspondingly weak, there is nothing to resist the expansion. Dark energy, the mysterious force driving the acceleration of cosmic expansion, operates essentially unopposed within the voids. Space inside a void expands faster than the cosmic average. The void grows larger. Its boundaries push outward, compressing the filaments on either side, thinning the walls, stretching the threads of the cosmic web toward a breaking point that will arrive in the deep future as a kind of cosmic unraveling. The voids are winning. They have always been winning. From the moment the first density fluctuations in the infant universe began, the process of gravitational amplification, the underdense regions have been growing emptier, while the overdense regions have been growing denser. The cosmic web is not a stable equilibrium. It is a dynamic system in which matter flows continuously from the voids into the filaments and from the filaments into the clusters, leaving the voids ever more thoroughly evacuated and the nodes ever more densely packed. The universe is sorting itself, concentrating its matter into an ever smaller fraction of its total volume, and the space left behind by that concentration, the voids that grow larger as the filaments drain, becomes more empty with every passing era of cosmic time. The architecture of isolation is not a fixed feature of the universe. It is a deepening one. Every billion years the voids are wider. Every billion years the filaments are thinner. Every billion years the distances between the dense structures where galaxies live are greater, and the emptiness between those structures is more absolute. The universe is not merely empty, it is becoming emptier, and the rate of that emptying is accelerating, driven by dark energy that grows more dominant as the density of matter continues to fall. What this means for any hope of connection between galaxies, for any possibility of crossing or communicating across the voids that separate them, is not a question whose answer improves with time. The void is not a temporary obstacle, it is a growing one. A barrier that is wider today than it was a billion years ago, and will be wider still a billion years from now, expanding outward in every direction at a rate that no technology conceivable under current physics can match. The cosmic web built the universe's isolation. Dark energy is deepening it. And what lies at the end of that deepening, what the universe looks like when the voids have grown wide enough and the filaments have thinned enough and the expansion has accelerated long enough, is a future so profoundly lonely that it makes the present emptiness look almost intimate by comparison. Forget for a moment everything you know about the limitations of current technology. Forget chemical rockets and ion drives and solar sails. Forget the Parker Solar Probe and its record-breaking 430,000 miles per hour. Forget every constraint imposed by the engineering realities of the 21st century and grant yourself the most generous possible scenario. Imagine a civilization that has solved every problem of propulsion. A civilization that has mastered energy at scales that dwarf anything humanity has ever contemplated. That has built a spacecraft capable of accelerating to a significant fraction of the speed of light. and sustaining that velocity across any distance required. Give that civilization a ship traveling at 90% of the speed of light. This is not a modest concession. A ship moving at 90% of light speed would be the most extraordinary machine ever conceived by any mind in any civilization at any point in the history of intelligence. It would cross the distance from the Earth to the Moon in under 2 seconds. It would reach the Sun in under 9 minutes. It would leave the solar system entirely within hours and arrive at the nearest star, Proxima Centauri, in just under 5 years. At 90% of light speed, the stars themselves become reachable within a human lifetime. The galaxy opens up. Distances that would otherwise require tens of thousands of years become manageable. Now, point that ship at the Andromeda Galaxy, the nearest large galaxy, our closest major neighbor, the galaxy that astronomers describe as practically adjacent by intergalactic standards. At 90% of the speed of light, the journey to Andromeda takes approximately 2.8 million years as measured by an observer watching from Earth. Not 28000 years, not 28000 years, 2.8 million years. There is a subtlety here that relativity introduces. When an object moves at a significant fraction of the speed of light time aboard, that object passes more slowly relative to time outside it. This is not a theoretical curiosity. It is a measured, confirmed, experimentally verified consequence of special relativity observed in particle accelerators in atomic clocks, carried aboard aircraft in the GPS satellites that must account for relativistic time dilation to maintain their accuracy. At 90% of light speed, the dilation factor, which physicists call the Lorentz factor, after the Dutch physicist Hendrik Lorentz, who first described it mathematically, compresses onboard time by roughly a factor of 2.3. A crew traveling at that speed would experience the passage of approximately 1.2 million years during the journey to Andromeda, while 2.8 million years elapsed on Earth. 1.2 million years of onboard time. The genus Homo has existed on Earth for approximately 2 to 3 million years. Every human ancestor who ever lived from the earliest tool-using members of our lineage through every subsequent species that eventually gave rise to modern humans fits within a span of time comparable to the onboard journey to Andromeda at 90% of light speed. The crew would experience a duration equal to the entire evolutionary history of the human family before their ship reached the other side. What if the ship traveled faster? At 99% of the speed of light, the Lorentz factor rises to approximately 7. The onboard travel time to Andromeda compresses to roughly 3500000 years. Better. Still longer than the entire span of modern Homo sapiens on Earth, but better. At 99.9% of light speed, the factor rises to approximately 22, and the onboard time drops to around 1130000 years. At 99.99%, the factor reaches about 70, and the onboard experience of the journey falls to roughly 3500000 years. No version of this calculation produces anything resembling a human-scale journey. And these velocities are not merely difficult to achieve, they approach the boundary of physical absurdity in terms of energy requirements. The kinetic energy of an object increases without limit as its velocity approaches the speed of light. At 90% of light speed, a single kilogram of matter carries a kinetic energy of approximately 117 quadrillion joules. That is the energy released by roughly 28 million tons of TNT, contained in 1 kilogram of moving mass. For a spacecraft massive enough to carry fuel, shielding, life support systems, and any meaningful payload, the total energy requirement climbs into figures that can only be expressed in terms of stellar output. The total energy consumption of all human civilization in a single year is approximately 580 exajoules. Accelerating a modest spacecraft of 1,000,000 kilograms to 90% of light speed, assuming perfect conversion efficiency with no losses, would require energy equivalent to more than 2,000,000 years of total human civilization's energy production. For a ship large enough to sustain a crew across a journey of hundreds of thousands of years, The energy budget climbs by orders of magnitude that make the comparison meaningless. You would need to capture and convert a meaningful fraction of a star's total output just to begin the acceleration phase, and then capture and convert it again to decelerate on the other side. The engineering does not merely exceed our current capabilities. It sits at a boundary where the laws of physics themselves begin to make the Enterprise look less like a challenge and more like a category error, like asking how fast you can dig a tunnel through the sun. But set the energy problem aside entirely. Pretend it is solved. Pretend the ship is built and fueled and launched and traveling at 90% of light speed toward Andromeda. The journey still takes 1.2 million years of onboard time. And this creates a problem that no amount of engineering ingenuity can address, because it is not an engineering problem. It is a biological one, and a civilizational one, and ultimately a philosophical one. No biological organism known to science can survive for 1.2 million years. No mechanical system built from any known material can remain functional across geological timescales without maintenance, repair, and replacement of components that wear, corrode, fatigue, and fail. The ship would need to be not a vessel but a world, a completely self-sustaining civilization capable of maintaining its technological infrastructure, its biological population, and its institutional memory across thousands of generations. The crew that departed would be the ancestors separated by 1 million years of isolated evolution in a metal shell crossing the void of the crew that arrived, and the civilization they left behind would be gone. 2.8 million years would pass on Earth between departure and arrival. Whatever culture launched that ship, whatever language its crew spoke, whatever values and ambitions drove the mission, all of it would be unrecognizable or extinct long before the first signal came back from the other side. The receiving civilization, assuming one still existed, would be as different from the launching civilization as we are from the first members of our genus who chipped flint into tools on the African savannah. There would be no one waiting for the report. The ship would arrive at a galaxy full of 1 trillion unfamiliar stars carrying the descendants of a civilization that no longer existed, reporting to a home that had no memory of sending them. The distance does not merely separate locations in space, it separates eras in time. Every intergalactic journey becomes simultaneously a voyage across space and a one-way trip through the deepest corridors of history. This is the scenario for Andromeda, the closest target, the best case. For galaxies beyond the local group, the numbers do not merely increase, they transform into something that the word large cannot contain. The Virgo cluster, the nearest major galaxy cluster, sits approximately 54 million light-years away. At 90% of light speed, the journey takes 60 million years, as measured from Earth, and roughly 26 million years of onboard time. 26 million years ago on Earth, the ancestors of modern elephants were just beginning to diverge from related lineages. The continents were in different positions. The oceans had different boundaries. The atmosphere had a different chemical composition. No primate even remotely resembling a human existed anywhere on the planet. The Coma cluster, one of the richest concentrations of galaxies in the nearby universe, lies approximately 320 million light-years distant. The onboard journey at 90% of light speed would consume over 130 million years. 130 million years ago, Earth was in the middle of the Cretaceous period. Dinosaurs dominated every terrestrial ecosystem. The first flowering plants were only just beginning to appear. Mammals existed, but they were small, nocturnal, and entirely unremarkable, with no hint in their biology or behavior that their distant descendants would one day build spacecraft and point them at the stars. No one is crossing that distance. No refinement of propulsion technology, no breakthrough in materials science, no advance in any engineering discipline changes the fundamental temporal cost of crossing 320 million light-years of expanding void. The numbers are not obstacles, they are verdicts. But the truly devastating blow to any hope of intergalactic connection does not come from distance or energy or biological limitation. It comes from something far more fundamental, something that operates not at the scale of engineering or biology, but at the scale of the universe itself. Space is expanding, not metaphorically, Not in the sense that galaxies are moving apart through a static background medium the way ships move apart across a calm sea. The fabric of space-time itself is stretching, increasing the physical distance between all points in the universe that are not bound together by gravity. Every second, the space between the Milky Way and every galaxy outside the local group grows larger. Every moment, the void gets wider. And the farther away a galaxy is, the faster the space between it and us expands. This relationship was first quantified by Edwin Hubble in 1929, who noticed that galaxies appear to be receding from us at velocities proportional to their distances. The proportionality constant, now called the Hubble constant, has been measured with increasing precision over the decades since. Its current value sits somewhere between 67 and 73 kilometers per second per megaparsec, depending on which measurement technique is used. The precise value is a subject of active debate among cosmologists, a disagreement known as the Hubble tension that remains one of the most significant unresolved problems in modern physics. But the existence of the relationship, the fact that recession velocity scales with distance, is not in dispute. What this means in practical terms is straightforward and devastating. For every megaparsec of distance, roughly 3.26 million light-years, the recession velocity of a galaxy increases by approximately 70 kilometers per second. A galaxy 10 megaparsecs away recedes at roughly 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7000 kilometers per second. A galaxy 10000 megaparsecs away recedes at 70000 kilometers per second. The speed of light is approximately 300,000 kilometers per second. At a distance of roughly 14 billion light-years, the recession velocity of a galaxy equals the speed of light. Beyond that distance, the space between us and those galaxies expands faster than light can cross it. This does not violate Einstein's special theory of relativity, which prohibits objects from moving through space faster than light. It says nothing about space itself expanding at any rate it pleases. The galaxies beyond this threshold are not moving through space at superluminal velocities. They are sitting relatively still in their local patch of space-time, while the space between us and them stretches faster than light can traverse it. The distinction is technically important. The consequence is absolute. The boundary beyond which light emitted today will never reach us, no matter how long the universe endures, is called the cosmic event horizon. It currently sits at approximately 16 to 18 billion light-years. That sounds like an enormous volume. In absolute terms, it is. But the observable universe extends 46.5 billion light-years in every direction. The region we could theoretically still touch if we departed at light speed right now is a small bubble embedded within the larger sphere of everything we can see. Current estimates suggest that only about 6% of the galaxies within the observable universe remain theoretically reachable. 6%. The other 94% are already gone, not destroyed, not moved. Gone in the only sense that matters for any practical or philosophical purpose. The space between us and them is expanding faster than light can cross it, and dark energy ensures that the expansion will only accelerate. Those galaxies exist, their stars are burning, their planets are turning. Whatever life or intelligence they contain is going about. Whatever business intelligence goes about when it exists in a universe, it cannot fully comprehend. And none of it can ever reach us. And none of us can ever reach any of it. They are visible but untouchable, observable but permanently sealed behind a horizon of expanding space that no signal, no ship, no message of any kind can penetrate. We can see them. Their ancient light is still arriving photons that began their journey billions of years ago, when those galaxies were closer and the expansion had not yet carried them past the horizon of reachability. But the galaxies themselves as they exist right now are beyond any form of contact forever. To make that number feel like what it is, consider the following. The Milky Way contains between 200 billion and 400 billion stars. It is one galaxy. The observable universe contains an estimated 2 trillion 94% of 2 trillion is approximately 1.88 trillion galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. Each of those stars may host planets. Each of those planets may host chemistry, biology, intelligence, civilization, art, grief, wonder, and every other condition that consciousness produces when it finds itself alive in a universe it did not ask to inhabit. 1.88 trillion galaxies, permanently beyond reach, today, right now. Not in some distant future, after dark energy has had additional billions of years to work. Now, the horizon is already drawn. The door is already closed on 94% of everything that exists within the volume our telescopes can survey. And the situation is worsening. Dark energy does not merely maintain the expansion of space, it accelerates it. The expansion is not running at a constant rate that will eventually be overcome by the gravity of the matter within the universe. It is speeding up, and the rate of acceleration shows no sign of decreasing. Every year that passes, the cosmic event horizon contracts slightly relative to the total observable volume. Galaxies that are currently just inside the boundary of theoretical reachability will, within millions of years, cross beyond it permanently. Entire galaxies are slipping past the horizon, continuously vanishing from the set of structures we could ever theoretically contact, joining the 1.88 trillion already gone. The reachable universe is shrinking. Not because the universe is getting smaller, because the expansion is accelerating faster than the boundary of reachability can keep pace with it. We are not exploring an expanding frontier. We are watching a closing door, and the door is closing faster with every passing year. Even within the 6% that remains theoretically reachable, the act of reaching is already functionally impossible for reasons that have nothing to do with the cosmic event horizon. A signal sent to the Virgo cluster travels for 54 million years before arriving. A reply, if anyone were listening, would take another 54 million years to return. A single exchange of information, one question and one answer, would consume 108 million years. No negotiation is possible. No scientific collaboration, no warning of any kind that could be acted upon within any civilization's functional lifespan. The communication delay does not merely make conversation difficult. It makes conversation, in any meaningful sense of the word, a fiction. And the signals themselves face one final enemy that the distance and the expansion have not yet accounted for. As a signal travels through expanding space, the expansion stretches its wavelength. A radio transmission sent at a specific frequency will arrive at its destination with a longer wavelength and lower energy than it started with, because the space it traveled through expanded during the transit. This is the same process that redshifts the light from distant galaxies, stretching the wavelengths of their photons toward the red end of the spectrum as the space between source and observer expands. For short distances, the effect is small and measurable. For intergalactic distances, it becomes crippling. A signal sent from a galaxy 1 billion light-years away would arrive with its wavelength stretched by roughly 7%. From 5 billion light-years stretched by roughly 40%. From 10 billion light-years more than doubled. At sufficient distances, the stretching pushes the signal below any conceivable detection threshold, smearing what began as a coherent transmission into a whisper indistinguishable from the random background noise of the cosmos. The universe does not merely make long-distance communication expensive. It garbles the message. It stretches meaning into silence. It takes the most powerful signal any civilization could generate, and given enough distance and enough time, reduces it to nothing. Distance, energy, time dilation, biological limitation, the expanding fabric of space-time, the cosmic event horizon, cosmological redshift. Each of these is independently sufficient to render intergalactic connection effectively impossible. Together, they constitute something stronger than an obstacle. They constitute a structural feature of reality, a set of interlocking constraints woven into the deepest physics of the cosmos that produces isolation as reliably and as inevitably as gravity produces orbits or nuclear physics produces stars. The universe was not designed with connection in mind. That phrasing is imprecise. The universe was not designed at all, but the effect is the same, as if it had been engineered specifically to ensure that its largest inhabitants remain forever separated from one another. The laws of nature, operating exactly as they were from the first moment of the Big Bang, produce a cosmos where 94% of all observable galaxies are already permanently beyond contact where the remaining 6% can never be physically reached within any biologically relevant time frame, and where even communication across the nearest intergalactic distances requires intervals longer than the span during which a complex life has existed on Earth. The local group is our island, the Milky Way Andromeda Triangulum, and approximately 130 smaller galaxies make up the only gravitational community we will ever belong to. These are the only galaxies close enough and massive enough that their mutual gravity overcomes the expansion of space. They will not fly apart. They will not recede beyond the cosmic event horizon. They are ours, and we are theirs, and everything beyond them is already leaving and will never stop. What that departure ultimately produces, what the universe looks like when it has finished the work of isolation that it began 13.8 billion years ago, is the darkest chapter in the story of everything that has ever existed. The Milky Way and Andromeda are falling toward each other. This is not a hypothesis. It is not a projection based on incomplete data or a theoretical prediction awaiting confirmation. It is a measured, confirmed, observationally verified fact, established through decades of spectroscopic analysis and refined most recently by proper motion measurements from the European Space Agency's Gaia spacecraft, which tracked the positions of stars in Andromeda's outer regions with sufficient precision to determine the galaxy's trajectory through space to an accuracy that was impossible with any previous instrument. Andromeda is approaching. At approximately 250,000 miles per hour, the two galaxies are closing the gap between them, drawn together by the combined gravitational pull of their hundreds of billions of stars, their vast dark matter halos, and the dozens of satellite galaxies orbiting each of them. The Large Magellanic Cloud, the most massive satellite of the Milky Way, has been shown by recent dynamical studies to carry enough mass to meaningfully influence the trajectory of the merger, adding complexity to predictions that had previously treated the collision as a simpler two-body problem. The timing and character of the merger have been subjects of ongoing refinement. A 2025 analysis incorporating updated Gaia data and accounting for the gravitational influence of the Large Magellanic Cloud found that a direct collision within the next 10 billion years carries a probability of roughly 50% lower than the near certainty that earlier models had suggested. A subsequent study published in early 2026, using the most recent proper motion measurements and improved models of the dark matter distribution in both galaxies, revised that probability upward to approximately 90%, with a median merger time of around 6.5 billion years. The question of exactly when and how the two galaxies will interact remains an active area of scientific investigation. The question of whether they will eventually merge does not. They will merge. The process will not resemble anything in ordinary human experience of collision. When two galaxies collide, the stars within them almost never actually strike one another. Stars are so small relative to the distances between them that two galaxies can pass directly through each other with only a tiny fraction of their stellar populations come level. What drives the drama of a galactic merger is not the collision of stars, but the collision of gravitational fields, the interaction of dark matter halos, the tidal forces that stretch and distort the spiral arms of both galaxies, pulling streams of stars into long, arcing bridges between the two. Structure. The merger will happen in stages. First contact, when the outer dark matter halos of the two galaxies begin to interpenetrate, is likely already occurring. The first close approach of the galactic disks themselves, when the visible spirals of the Milky Way and Andromeda swing past each other in a gravitational embrace that will dramatically distort the shape of both, will happen sometime in the next several billion years. That first pass will not produce an immediate merger. The galaxies will swing past each other, pulled apart again by their relative velocities, and then drawn back together for a second pass and possibly a third, each approach more disruptive than the last, each one stripping more stars into tidal streams and heating more gas into starburst regions where new stars form at rates far higher than either galaxy currently sustains. Eventually, Over a period of perhaps 1 billion years following the first close approach, the two systems will lose enough orbital energy to their surrounding dark matter halos that they can no longer escape each other. They will spiral together, their structures increasingly intermingled, their supermassive black holes drawn toward each other through the dense stellar environment of the merged core, and they will settle into a single massive structure. Astronomers have given this future galaxy a name, Milkomeda. Milkomeda will be an elliptical galaxy, its elegant spiral arms erased by the violence of repeated mergers and replaced by a smooth, featureless oval of stars orbiting the combined center in random directions. It will be enormous, containing the stellar populations of both the Milky Way and Andromeda, along with every satellite galaxy and dwarf companion that falls within its gravitational reach during the merger process. It will host a supermassive black hole at its center, formed by the eventual coalescence of the two existing central black holes, a merger that will itself release gravitational waves of extraordinary power, detectable in principle across billions of light-years of space. By any measure, Milkomeda will be a spectacular object, a giant elliptical galaxy containing perhaps 1 trillion stars, settled into a state of relative stability after billions of years of gravitational turbulence. Its stellar populations, a thoroughly mixed archive of the two great spirals that once existed separately in this corner of the universe. And it will be alone. Not metaphorically alone, not alone in the way a remote island is alone, surrounded by an ocean that other ships could cross if they chose to. Alone in a way that has no precedent in the current universe. Alone in a way that makes the present isolation of the Milky Way look by comparison almost sociable, because by the time Milkomeda has fully formed the universe around, it will have transformed into something unrecognizable from the cosmos we inhabit today. Consider the timeline. The first close approach of the Milky Way and Andromeda is expected in roughly 4 to 5 billion years. The full merger, the settling of both galaxies into a single stable structure, will take perhaps another 1 billion years beyond that. Call it 6 billion years from now before Milkomeda exists as a coherent object. That is a long time, long enough for our sun to exhaust its hydrogen fuel, swell into a red giant, and begin the process of shedding its outer layers that will eventually leave behind a cooling white dwarf. Long enough for the solar system as it currently exists to cease to exist in any recognizable form. Long enough for every star currently visible in the night sky to have aged significantly, many of them having already burned through their fuel and died. But 6 billion years is not the end of the story. It is barely the beginning of the transformation. The universe is currently 13.8 billion years old. In 6 billion years, it will be approximately 20 billion years old. The cosmic event horizon will have contracted further. Galaxies that today sit just inside the boundary of theoretical reachability will have receded beyond it. The Virgo cluster, the nearest major galaxy cluster already unreachable in any practical sense, will have moved farther still, its recession velocity increased by the continued acceleration of cosmic expansion, its distance from the local group grown by hundreds of millions of additional light-years. The process does not stop there. Dark energy does not plateau. The acceleration of cosmic expansion continues without any mechanism in current physics that would slow or reverse it. And as the universe ages beyond 20 billion years, beyond 50 billion, beyond 100 billion, the consequences of that acceleration accumulate into something that transforms the observable universe into a place of absolute and permanent darkness. Within approximately 100 to 150 billion years from now, every galaxy outside the local group will have receded beyond the cosmic event horizon. Everyone. The Virgo cluster, with its thousands of galaxies and its immense concentration of mass. The Coma cluster, one of the richest structures in the nearby universe. The great walls and filaments of the cosmic web that currently stretch across hundreds of millions of light-years. The supervoids and their sparse populations of isolated galaxies. Every structure that currently exists beyond the gravitational boundary of the local group will have been carried past the horizon of reachability by the accelerating expansion of space, their light redshifted to wavelengths so long that no instrument could detect them, their recession velocities so far beyond the speed of light that no signal could ever bridge the gap. The sky for any observer within Milkomeda at that epoch will contain one thing: Milkomeda itself. Its stars, its stellar remnants, the white dwarfs and neutron stars and black holes left behind by generations of stellar evolution. The faint glow of its oldest surviving stars, red dwarfs burning so slowly and so dimly that they will still be shining billions of years after the last sun-like star has gone dark. And beyond the galaxy's edge, in every direction, in every quadrant of the sky, in every wavelength accessible to any instrument, nothing. Not the darkness of a cloudy night where stars are hidden behind weather, and the observer knows the sky will clear. A structural, permanent, physically absolute darkness extending in every direction without limit. A darkness that is not the absence of light that has not yet arrived, but the permanent absence of light that can never arrive, because every source of light beyond the galaxy's gravitational boundary has been carried past the horizon by an expansion that will never reverse. Think carefully about what an observer within Milkomeda at that epoch would be able to know about the universe. They would know their galaxy, its stars, their distances, their compositions, their motions. They would know the physics of stellar evolution, of gravity, of electromagnetism, of nuclear forces. They would be able to develop mathematics and logic and every branch of science that depends on observations available within the galaxy itself. They might be extraordinarily sophisticated, their understanding of local physics rivaling or surpassing anything humanity has yet achieved. But they would have no way of knowing that the universe is expanding. The measurement of cosmic expansion depends on observing distant galaxies and detecting their recession velocities through the redshift of their light. With no galaxies beyond Milkomeda visible, there is no data from which to infer expansion. The universe would appear from inside Milkomeda to be static, not expanding, not contracting, simply there. A single galaxy in an infinite, featureless, unchanging void. They would have no way of discovering the Big Bang. The cosmic microwave background radiation, the faint thermal afterglow of the universe's hot, dense beginning, is currently detectable across the entire sky at a temperature of approximately 2.7 Kelvin. It represents the most direct observational evidence for the Big Bang available to any observer in the current universe. But the CMB is not a permanent fixture. It is a relic of the early universe, whose photons are being continuously redshifted by the expansion of space, their wavelengths growing longer and their energy growing lower with every passing era. Within 100 billion years, the CMB will have been redshifted to wavelengths so long and intensities so low that no conceivable instrument could distinguish it from the noise floor of the cosmos. It will have effectively ceased to exist as an observable phenomenon. The evidence for the universe's beginning will be gone. They would have no way of inferring the existence of the cosmic web. The great filaments and walls and voids that define the large-scale structure of the universe are visible today because we can observe galaxies at cosmological distances and map their three-dimensional distribution. With nothing beyond Milkomeda to observe, there is no data from which the cosmic web could be inferred. The entire architecture of the universe, the structure that took billions of years of gravitational physics to produce, and that tells the story of how every galaxy in existence came to be. Where it is would be invisible and unknowable. A civilization arising within Milkomeda at that epoch would look outward and see a universe that contains exactly one galaxy, surrounded by infinite empty space, with no evidence of expansion, no evidence of a beginning, and no evidence of any structure beyond their own galactic boundaries. They would develop a cosmology. They would construct models of the universe based on the available data. And those models would be wrong in the most profound possible way, not because of any failure of intelligence or rigor, but because the universe would have removed the evidence required to get the right answer. The expansion that created the CMB would have erased the CMB. The large-scale structure that reveals the universe's history would have receded beyond detection. The very processes that produce the cosmos would have systematically destroyed the observational record of their own operation. The universe erases its own history. It grants observers a brief window during which the evidence of its origins and its architecture is visible, and then it closes that window, carrying the evidence past the horizon on the tide of accelerating expansion, leaving behind emptiness that offers no clues about the grander reality that once surrounded it. We live inside that window. This moment, this era in the universe's history is the period during which the evidence is still available. The cosmic microwave background is still detectable. The cosmic web is still mappable. Galaxies at distances of billions of light years are still observable, their ancient light still arriving, still carrying information about the universe's history and structure. The expansion is still measurable, because there are still objects close enough to observe whose recession velocities reveal the relationship between distance and velocity that Hubble first identified nearly a century ago. Everything that defines our current understanding of cosmology, the Big Bang, the age of the universe, its geometry, its composition, the existence of dark matter and dark energy, the large-scale structure of the cosmic web depends on observations that are only possible during this window. And the window is closing, not closing rapidly by human standards. The evidence will remain accessible for billions of years yet, but it is closing. Every year that passes the CMB redshifts to slightly longer wavelengths. Every year the most distant observable galaxies recede slightly farther past the edge of detectability. Every year the cosmic horizon contracts slightly relative to the total volume of the observable universe. The window does not slam shut. It narrows slowly but continuously and without reversal, driven by an expansion that has been accelerating for roughly the last 5 billion years, and that shows no sign of stopping. What this means is something that most people who think carefully about cosmology find genuinely unsettling in a way that goes beyond the usual discomfort produced by the scale of the universe. We are not at the beginning of cosmic understanding. We are at the peak of it. The universe contains more observable evidence about its own nature, right now at 13.8 billion years of age, than it will ever contain again. Every future era will have access to less information than the present one. Every civilization that arises in the deep future will know less about the universe than a civilization with our current technology knows today. Not because future civilizations will be less intelligent or less curious, but because the universe will have taken the evidence away. We are the most informed observers the universe will ever produce, and we are only just beginning to understand what we are looking at. The stars within Milkomeda will not burn forever. The most massive stars will die within millions of years of forming their lives, brilliant and brief ending in supernovae that seed the galaxy with heavy elements. Stars like the Sun will burn for billions of years before exhausting their fuel and collapsing into white dwarfs. The smallest stars, the red dwarfs, are so miserly with their fuel that some of them will burn for trillions of years, long outlasting every other stellar type, and eventually becoming the last fires in a darkening galaxy. But even they will go out. In the deep future, beyond any timescale that human intuition was built to navigate, the last red dwarf in Milkomeda will exhaust its hydrogen and cool into darkness. The galaxy will still exist, its mass still present, its gravity still binding its contents together, but it will be a galaxy of remnants. White dwarfs slowly cooling toward black dwarfs, objects so cold they emit no detectable radiation, neutron stars spinning down to stillness, black holes growing imperceptibly as they absorb the diffuse gas, and occasional stellar remnant that drifts within their gravitational reach. And surrounding all of it in every direction, the same absolute darkness that has existed beyond the galaxy's boundary since every other galaxy in the universe crossed the horizon billions of years before. The universe ends not with a dramatic collapse or a catastrophic explosion, but with a silence so complete and so permanent that even the concept of ending becomes meaningless. There is no moment when it stops. There is only the slow, continuous, irreversible deepening of a darkness that has been growing since the first fraction of a second after the Big Bang, when the quantum fluctuations that would eventually become voids first appeared in the fabric of the infant cosmos. The darkness was always the destination. The galaxies, the stars, the planets, the oceans and atmospheres and chemistries and biologies that briefly inhabited them, all of it was a temporary interruption. A brief, improbable, extraordinary departure from the baseline condition of the universe, which is, and has always been, at its most fundamental level, cold and dark and empty and alone. This is not a cause for despair. Or perhaps it is, and the despair is the appropriate response, and sitting with it rather than deflecting it is the more honest choice. But there is something else here too, something that the scale and the darkness and the deepening isolation make visible rather than obscure, if you are willing to look at it directly. And that is the subject of what remains to be said. There is a photograph that changed everything. Not a photograph of a galaxy or a nebula or a star field. A photograph of a pale blue dot, a tiny smear of color, suspended in a beam of scattered sunlight surrounded on all sides by absolute blackness. Voyager 1 took it on the 14th of February 1990 at the request of Carl Sagan from a distance of approximately 3.7 billion miles from Earth. In that image, the entire Earth, every mountain and ocean and city and civilization that has ever existed, occupies less than a single pixel. Sagan wrote about that image with a precision of feeling that has not been surpassed in the decades since. He noted that every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived out their lives on that mote of dust, suspended in a sunbeam. He was talking about scale, about the smallness of the Earth relative to the solar system, about the humility that the image demands of anyone who looks at it honestly. But Voyager, 1 at 3.7 billion miles, had not even left the solar system yet. It was still inside the bubble of the sun's magnetic influence. The nearest star was still more than 4 light-years away. The Milky Way was still 1,000,000 light-years across. Andromeda was still 2.5 million light-years distant. The Virgo cluster was still 54 million light-years away. The cosmic event horizon was still 16 billion light-years out and beyond it, still sealed behind an expanding wall of space that no signal could penetrate, still burned 1.88 trillion galaxies that we can see but never touch. Sagan was talking about a smallness that, measured against the true scale of the universe, was itself incomprehensibly large. This is the vertigo that honest cosmology produces. Not a single step down from the familiar to the large, but a cascade of steps, each one dissolving the floor that the previous step had established, each one revealing that what felt like the bottom was itself suspended over an abyss at greater depth. You think you have grasped the scale of the solar system and then the galaxy arrives. You think you have grasped the galaxy and then the local group arrives. You think you have grasped the local group and then the observable universe arrives. And then the reachable universe arrives 6% of the observable, and then the timeline arrives, shrinking that 6% further with every passing year. And then the deep future arrives, and the window closes and the darkness deepens. And somewhere at the bottom of all of it is a question that the numbers alone cannot answer. What does it mean? Not what does it mean in the sense of a cosmic purpose or a divine intention. The universe offers no evidence of either. But what does it mean for the only things in the known universe that are capable of asking the question? What does it mean for minds? For consciousness? For the strange, improbable, brief condition of being a creature that can measure the distance to Andromeda and feel something about the answer? Begin with the paradox that sits at the center of everything this story has been building toward. We know more about the universe than any previous generation of humans, more than any previous generation of any species. As far as we can determine, we have mapped the cosmic microwave background to a precision of 1 part in 100,000. We have measured the expansion rate of the universe and found that it is accelerating. We have detected gravitational waves from merging black holes 1 billion light-years away. We have imaged the shadow of a supermassive black hole 6.5 billion times the mass of the Sun at the center of a galaxy 55 million light-years from Earth. We have found thousands of planets orbiting other stars and identified the chemical signatures of their atmospheres. We have traced the large-scale structure of the cosmic web across billions of light-years and confirmed that the universe's matter is organized into filaments and voids on scales that make every human structure look like a rounding error. We know with extraordinary precision that 94% of the observable universe is already permanently beyond our reach, and that knowledge changes nothing about the distance. This is the cruelty buried inside the beauty of modern cosmology. Understanding the universe in exquisite detail does not bring any part of it 1 meter closer. Knowing that the Andromeda Galaxy contains 1 trillion stars and a supermassive black hole and thousands of star clusters and billions of planetary systems does not reduce the 2.5 million light-years between here and there by a single kilometer. Knowing that the cosmic event horizon sits at 16 billion light-years and that 1.88 trillion galaxies lie beyond it does not open a door in that horizon through which anything could pass. Knowledge and access are completely decoupled. We are in the most precise possible sense, the most informed prisoners any universe has ever best. We can see our cell with extraordinary clarity. We can measure its walls with instruments of remarkable sensitivity. We can calculate exactly how thick those walls are, and exactly how fast they are thickening, and none of that understanding loosens the walls by a fraction of a millimeter. Most people, when they encounter this situation, reach instinctively for one of 2 responses. The first is dismissal. The distances are so large and the time scales so incomprehensible that the isolation feels abstract academic, too remote from ordinary life to carry genuine emotional weight. Yes, we cannot reach other galaxies. We cannot reach other stars either, not within any individual human lifetime, not with any technology we currently possess. And yet this does not produce existential despair on a daily basis. Life continues. The inability to visit Andromeda does not prevent anyone from having breakfast or raising children or finding meaning in the ordinary texture of human experience. The vastness is real, but it is also irrelevant to the actual business of living. This response is understandable. It is also, if examined carefully, a form of looking away rather than looking at. The second response is inflation. The distances are large, but the universe is also large enough to contain whatever is needed to make the situation feel less bleak. Perhaps there are other universes. Perhaps the laws of physics that prevent faster-than-light travel are not fundamental but contingent, and some future understanding will reveal a way around them. Perhaps the 1.88 trillion unreachable galaxies are matched by 1.88 trillion reachable ones in some adjacent reality we have not yet discovered. Perhaps the isolation is temporary, a condition of our current technological infancy that a sufficiently advanced civilization will eventually transcend. This response is also understandable. It is also a form of looking away dressed in the language of optimism rather than the language of indifference. The honest response, the one that neither dismisses the isolation nor inflates it away, is harder. It requires sitting with the numbers without flinching. It requires letting the distances be what they are, letting the verdict be a verdict, letting the closed door be closed, and then asking what remains after that acceptance. What remains is this. The universe is structured to isolate its galaxies from one another. This is not a flaw in the design, it is the design. The same gravitational physics that built the Milky Way also evacuated the space around it. The same dark energy that is carrying the Virgo cluster past the cosmic horizon is also responsible for the accelerating expansion that has stretched the universe to its current size, diluting the density of matter to the point where galaxies could form at all. The isolation and the existence are products of the same physics. You cannot have one without the other. And within that isolated existence within the local group and the single galaxy that the local group will eventually become, something happened that the laws of physics did not require, but also did not prevent. Matter organized itself into complexity. Not everywhere, not inevitably, not as a guaranteed outcome of any physical process, but as one possible outcome among many achieved in at least one location through a sequence of events whose probability is still a subject of profound scientific uncertainty. Hydrogen and helium, the simplest atoms produced by the Big Bang, collapsed under gravity into stars. Those stars fused heavier elements and scattered them across space when they died. Those heavier elements, carbon and oxygen and nitrogen and iron, and dozens of others, found their way into new stellar systems and coalesced into planets. On at least one of those planets, in an unremarkable spiral arm of an ordinary galaxy, in a small, gravitationally bound group on the edge of a cosmic void. The chemistry of those heavy elements produced something that had never existed before, anywhere in the 9 billion years of cosmic history that preceded it. Something that could ask where it was. The question of whether this happened elsewhere, whether other planets in other galaxies also produced chemistry complex enough to generate consciousness and curiosity, is one that the distances themselves prevent us from answering. The nearest large galaxy is 2.5 million light-years away. Even if it teems with civilizations, even if every star in Andromeda hosts a world of conscious beings capable of mathematics and music and grief and wonder, the gap between us and them is so wide and the tools available for bridging it so utterly inadequate that we will never know, not in any practical, confirmable response-receiving sense. The question of whether we are alone in the universe cannot be answered by looking at other galaxies. The isolation is too complete, the distance is too enormous, the communication delays too ruinous. Whatever answer exists out there 2.5 million light-years away, or 54 million, or 320 million, it is an answer we will never receive. What we can say with confidence is what we know about this galaxy. The Milky Way contains between 200 billion and 400 billion stars. Data from the Kepler and TESS missions suggests that the majority of those stars host planetary systems. Conservative estimates of the fraction of those planets that might support liquid water, combined with conservative estimates of the fraction of such worlds where chemistry could become biology and biology could become complexity, and produce numbers ranging from plausibly common to extraordinarily rare, depending on assumptions that remain deeply uncertain. We do not know whether life is a routine product of chemistry, given the right conditions, or whether it is a once-in-a-universe accident that happened to us and nowhere else. We know it happened here. That knowledge, that single confirmed data point in an otherwise empty observational record, is either one of the most ordinary facts about the universe or one of the most extraordinary. We cannot tell which because we have nothing to compare it to. We are trying to assess the significance of a phenomenon using a sample size of 1. It is the most important question in science, and it may be permanently unanswerable, not because we lack the intelligence to find the answer, but because the universe has placed every potential data point beyond the reach of any instrument we could build in any time frame that matters. The isolation is not just physical, it is epistemic. It does not merely prevent us from visiting other galaxies. It prevents us from knowing whether the thing that makes our existence feel significant, the consciousness that looks up and wonders, is a unique accident or a common feature of a universe too large and too isolated for any of its parts to know what the others contain. And yet, there is something that the isolation cannot touch, something that the expanding void and the cosmic event horizon and the 1.88 trillion unreachable galaxies cannot diminish, no matter how precisely the distances are measured or how thoroughly the physics of expansion is understood. The fact of the asking, whatever the universe is, whatever its scale and its emptiness and its structural indifference to the existence of anything within it, it produced in at least one location something capable of measuring it, something that can look at a faint smudge of light in an autumn sky and know that it is a galaxy of 1 trillion stars 2.5 million light-years away. Something that can calculate the recession velocity of objects at the edge of the observable universe and understand that those objects are permanently beyond contact. Something that can trace the history of the cosmos from the first fraction of a second after the Big Bang to the final cooling of the last red dwarf in a future so remote that no human intuition can hold it. The universe spent 9 billion years producing the raw materials. It spent another 4.5 billion years arranging those materials into a world capable of sustaining the chemistry of life. It spent another 3.5 billion years allowing that chemistry to complexify into biology, and biology into nervous systems, and nervous systems into the thing that right now, in this moment, is reading these words and feeling something about the distance to Andromeda. That process was not inevitable. Nothing in the laws of physics required it. The universe could have produced a cosmos of stars and galaxies and black holes and gravitational waves without ever producing a single mind capable of knowing that any of it existed. The laws of physics permit consciousness but do not demand it. And yet here it is. Here you are, sitting inside one galaxy among 2 trillion, in the 6% of the observable universe that remains theoretically reachable during the narrow window of cosmic time, when the evidence of the universe's history is still visible, when the cosmic microwave background is still detectable, when the cosmic web is still mappable, when the light from distant galaxies is still arriving with information about the universe's past encoded in its wavelength and intensity. You are not merely an observer of the universe. You are the universe observing itself. A temporary concentration of atoms that were forged in stellar interiors and scattered by stellar deaths and gathered by gravity into a world and animated by chemistry into a mind now looking outward at the void from which all of those atoms originally came, and understanding with a precision that would have been impossible even a century ago exactly how vast and how empty and how structurally isolated that void actually is. The void does not know you are looking at it. The expanding space does not notice the minds it has produced. The cosmic event horizon does not pause for the civilizations it is sealing into their galactic islands. The universe is indifferent in the most literal possible sense. Not hostile, not benevolent, not interested, simply operating according to rules that were set in the first instant of existence and that have been producing their consequences ever since without variation or mercy. And within that indifference, against the backdrop of that isolation, knowing the distances and the time scales and the physics with a clarity that no previous generation possessed, you are here. That is not nothing. It may be the least nothing thing in the known universe. Look up tonight. Find a dark place if you can, far enough from the nearest city that the sky has recovered some of its depth, that the fainter stars have become visible again, that the band of the Milky Way has resolved itself from a rumor into a presence. Stand there for a moment before you try to think anything, before you reach for context or scale or the numbers that this story has been accumulating across everything you have read so far. Just look. What you will see in that first unmediated moment of looking is light. Light that left its sources years ago and decades ago and centuries ago and millennia ago, converging on the particular point in space that your eyes happen to occupy at this particular moment in the history of the universe. Light from stars that are still burning and light from stars that have already died, both arriving simultaneously at your retina, indistinguishable to your visual system, equally present in the darkness above you. The sky you are looking at is not a single moment. It is a palimpsest of moments layered across thousands of years of transit time, all of them arriving at once, all of them pretending to be now. And somewhere in that sky, if you know where to look, if the night is clear enough and your eyes have adjusted sufficiently, there is a faint smudge of light in the direction of the constellation Andromeda, pale, unremarkable, easily overlooked by anyone not specifically searching for it. A wisp of photons so faint that light pollution in most inhabited places erases it entirely, leaving no hint of its existence to anyone who has not been told where to look and what to look for. Those photons left Andromeda 2.5 million years ago, not as a metaphor, not as an approximation, as a physical fact as precisely measured as any fact in the history of science. The light entering your eye from that smudge in the sky completed a journey of 14.7 quintillion miles, crossing a void containing approximately 1 atom per cubic meter, traveling at 1.860000 miles per second, without pause or deviation, to arrive at the exact location your eyes occupy at the exact moment you are looking. It passed through 2.5 million years of cosmic time, during which your entire species rose from its first tentative steps out of Africa to its current position as the only known species capable of understanding where that light came from. And it arrived. That is where this story ends. Not with a resolution of the distances, because the distances do not resolve. Not with a solution to the isolation, because the isolation is not a problem awaiting a solution. It is the architecture. It is the nature of the place. The void between galaxies is not a challenge to be overcome by a sufficiently advanced civilization. It is a structural feature of reality as fundamental and as permanent as the speed of light or the charge of an electron. The 94% of the observable universe already beyond the cosmic event horizon will not become reachable. The 1.88 trillion galaxies sealed behind the expanding wall of space-time will not send their signals through. The Boötes void will not fill. The intergalactic medium will not become denser. Dark energy will not reverse. The window of cosmic observability will not stop closing. These are not temporary conditions, they are the universe. But here is what the numbers, for all their precision, cannot fully capture. Here is what gets lost in the cascade of light years and recession velocities and event horizons and the deep futures measured in trillions of years. The light still arrives. Across 2.5 million light-years of near-perfect vacuum, across a void containing a single hydrogen atom per cubic meter, across an emptiness so extreme that the most sophisticated vacuum chambers ever built by human hands would register as dense, crowded environments by comparison across a distance that the fastest object humanity has ever constructed would need 4 billion years to cross the light from Andromeda. Still arrives. It arrives every night. It has been arriving since before our species existed. It will continue to arrive for billions of years after we are gone, falling on whatever surfaces exist to receive it, whether or not any of those surfaces contain the kind of chemistry that can know what it is receiving. The universe is not silent. It is full of signals that the distances make it impossible to answer, full of light from sources that the expansion makes it impossible to reach, full of information about its own history and structure that the closing of the observational window will eventually make it impossible to read. But right now, in this era, in this narrow band of cosmic time during which the evidence is still present and the window is still open and the light is still arriving, the universe is speaking in the only language it has: distance. And the light that crosses it, every photon reaching your eye from a distant star, is a message that the star did not intend to send and that you were not meant to receive. The universe has no intentions. Stars do not aim their light at specific destinations. Photons do not travel with purpose, but they travel, and some fraction of the light emitted by every star in every direction finds its way, after years or centuries or millions of years of transit, to a surface that can absorb it. Sometimes that surface is a rock. Sometimes it is an ocean. Sometimes, in this brief and improbable era of cosmic history, it is an eye connected to a brain that can understand what it is absorbing. That is the most extraordinary thing the universe has produced. Not its size. Size is not an achievement. The universe is large because the laws of physics that govern expansion have been operating for 13.8 billion years, and largeness is what those laws produce over that duration. The size of the universe is as unremarkable from a physical standpoint as the size of a crystal growing in a supersaturated solution. It is simply what happens when the relevant laws operate over the relevant timescales. What is not simply what happens, what is not a routine consequence of any known law of physics operating over any known timescale, is the existence of something inside the universe that can measure the universe. That can look at the faint smudge of Andromeda in the autumn sky and know that it is a galaxy of 1 trillion stars 2.5 million light-years away. That can calculate the recession velocity of galaxies at the edge of the observable universe and understand that those galaxies are permanently beyond contact. That can trace the history of the cosmos from the first fraction of a second after the Big Bang to the final cooling of the last stellar remnant in a future so remote that the number of years required to describe it contains more digits than there are atoms in the observable universe. The universe spent 9 billion years producing the heavy elements required for the chemistry of life. It spent another 4.5 billion years assembling those elements into a world and allowing that world to develop the conditions suitable for biology. It spent another 3.5 billion years allowing biology to complexify into the particular arrangement of matter that is reading these words right now. And at no point in that entire sequence did the laws of physics require any of it to happen. Chemistry could have remained chemistry. Biology could have remained simple. Nervous systems could have remained simple sensory organs responding to local stimuli without ever developing the capacity to model the universe beyond their immediate environment. They did not remain simple. Something happened that the laws of physics permitted but did not mandate. Something happened that required the right star in the right location, with the right planet at the right distance, with the right chemistry at the right time, across a sequence of contingencies so specific that the probability of their conjunction, if calculated honestly, would produce a number that looks like an argument against the thing having happened at all, and yet it happened. You are the evidence that it happened. Your existence is simultaneously the most ordinary and the most extraordinary fact in the known universe. Ordinary because you are made of the same atoms that comprise every other object in the cosmos, forged in stellar interiors and scattered by stellar deaths, and gathered by gravity into a world, and animated by chemistry into life. Extraordinary because those atoms in you have arranged themselves into a configuration capable of knowing what they are, and where they came from, and how far away the nearest large galaxy is. The void does not know any of this. The expanding space is indifferent to the minds it has produced. The cosmic event horizon does not pause for the civilizations it is sealing into their galactic islands. The 1.88 trillion galaxies beyond the horizon continue doing whatever galaxies do, burning their stars and evolving their structures, and perhaps producing their own brief concentrations of complexity that look outward and find the same darkness we find when we look beyond our own. Horizon. We will never know. The isolation ensures that we will never know, not because the answer does not exist, but because the distance between us and any possible answer is too great for any signal to bridge within any time frame that matters to either the sender or the receiver. The universe contains the answer to the question of whether we are alone, encoded somewhere in the light of 2 trillion galaxies, and it has arranged those galaxies at distances that make the answer permanently unreachable. This is the universe, not the universe we might have wished for, not the universe that a mind designing for the comfort of its inhabitants would have built. The universe as it actually is, vast beyond any intuition's ability to hold, empty beyond any analogy's ability to capture, structured at its most fundamental level to ensure the isolation of every galaxy from every other galaxy, indifferent to the existence of the minds it has produced, and yet capable through no intention of its own, producing those minds, of producing the very things that find the vastness overwhelming, that feel the isolation as something more than a physical fact, that look up at the faint smudge of Andromeda and experience something that the laws of physics have no name for. Call it awe, call it the particular vertigo that comes from understanding even partially, even approximately, even with limitable simplifications and analogies and comparisons that human language requires the actual scale of the place you inhabit. Call it the recognition that the universe is not arranged for your benefit, and that it is magnificent anyway. Call it the knowledge that the light arriving at your eye from Andromeda traveled 2.5 million years to get there, and that nothing in the physics of that journey required it to find an eye capable of knowing what it had crossed to reach. But it found one. In the deepest void, in the most structurally isolated corner of the most isolated galaxy group in the reachable universe, on the 3rd planet of an unremarkable star, in an outer spiral arm of an ordinary barred spiral, in the brief and improbable window of cosmic time during which the evidence of the universe's history is still visible, and the light from distant galaxies is still arriving, there is something looking up, something that knows the distance, something that feels the weight of the void not as a number but as a presence, as the particular silence that comes from understanding that the darkness between the stars is not merely dark but structured, organized by the physics of the early universe into a pattern of isolation so complete and so permanent that the galaxies themselves, for all their billions of suns, amount to campfires burning alone in a darkness that stretches farther than light has traveled since the beginning of time. The campfires are real. Their warmth is real, even though it does not cross the void between them. Their light is real, even though it arrives at neighboring galaxies as a faint smudge rather than a beacon. The complexity they harbor, the chemistry and biology and consciousness that some of them have produced in the narrow temperature ranges and stable chemical environments of their planetary systems, is real. The questions that consciousness asks when it finds itself looking outward from one of those campfires into the surrounding darkness are real. The darkness is also real, and it is vast beyond any measure that comfort permits. And it is growing, and it will keep growing, driven by a force whose nature remains one of the deepest unsolved problems in physics, until every campfire outside our own gravitational family has been carried past the horizon and the sky above Milkomeda contains nothing but the light of its own stars, burning against a darkness so absolute and so permanent that no future observer within it will have any way of knowing that other fires ever burned. But that is the deep future. Right now the light is still arriving. Right now the window is still open. The cosmic microwave background is still detectable. The cosmic web is still mappable. The Andromeda Galaxy is still visible on a clear autumn night, a faint smudge of photons that left 1 trillion stars 2.5 million years ago and crossed the void and arrived at a planet where something had developed against all physical necessity, the capacity to know what they were. Right now, you are here, in the only moment the universe has ever produced that contains both the knowledge of the distances and the ability to feel something about them. In the only era of cosmic history during which the evidence of the universe's origins is still visible and the light from distant galaxies is still arriving with their ancient messages intact. In the only galaxy group you will ever belong to, on the only world you will ever inhabit, in the only body that will ever carry the particular arrangement of atoms and memories and questions that constitutes you. The void is real, the isolation is permanent, the darkness is growing, and the light is here now, arriving from 2.5 million light-years away, crossing the loneliest distance in the universe, to fall on a world that somehow, against every reasonable expectation of physics and probability, learned to look back. That is not a small thing. In a universe built almost entirely from silence, it may be the only thing that matters at all.